Hello, my name is Dustin and welcome to MopBots. This is a companion video for the super simple LED switch circuit we made for one of our Introduction to PIC Programming Using C project series. Our goal for this series is to learn how to program a PIC 18F4525 microcontroller using the C programming language to control an LED with a couple of switches. There are 3 articles associated with this project on the MopBots website. The first being the Preliminaries, where we discuss some basics like what a PICkit programmer is and why we need one to flash our code to the PIC microcontroller. Here, we also discussed about the PIC 18F4525 microcontroller and Microchip's MPLAB software we'll use to program the microcontroller. We even get familiar with the hexadecimal number system to understand some of the code we'll write for this project. This is a companion video for part 2 of this series. This is the only video made for this series. In this video, we'll get into building the prototype circuit and go over things like the parts and tools we used. This video is not going to be a follow-along build video, but an overview of the circuit that's already been made on the breadboard. I'll go over every component and jumper along the way. All the build details can be found on the article associated with this video. That's part 2 of this Introduction to PIC Programming Using C, programming a super simple LED switch. In this video, we'll also discuss about power supplies and get into what a flowchart is and the need to use one. We'll also go over the schematic of the super simple LED switch, and we'll even go over all the pins we'll be using on the PIC 18F4525. For part 3 of this series, we finish our discussion by going over the code line by line and how it works. We even go over some common errors when trying to connect the PICkit device to the MPLAB IPE. We'll even test the circuit at the end to make sure that it works properly. These discussions for part 3 of this series are shared in our article at the MopBots website, except for the testing of the circuit, where I'll show it working here. Even though I will not be going over the code here in this video, I have thoroughly gone over the code in both parts 1 and 3 of this series at the MopBots website. I've even shared extremely detailed information on troubleshooting common errors when trying to connect a PICkit device to the MPLAB IPE. There's loads of information available to you in all parts of this series, and I highly recommend you go check out those articles at our website. I'll leave all the appropriate links in the description of this video. I'll even share with you the links you may find the complete code for this project. Trust me, you probably won't find such easily available information that walks you through step by step as we did at MopBots. For this project, I've programmed the PIC 18F4525 microcontroller to wait for a user to press either of the 2 switches that will control whether a red LED is to be turned on or to be turned off. The circuit uses very few components to accomplish this task. All we need is a breadboard, some jumper wires of varying colors and sizes, a PIC 18F4525 microcontroller, a few momentary push-button switches, a red LED, a few resistors, and a capacitor. The tools we'll need are a PICkit in-circuit debugger programmer. I used an older PICkit 3 version, a universal programmer seat board adapter, Microchip's MPLAB software tools, and a 5-volt power supply. That's it. I go over exactly how to use the older version of the PICkit 3 in-circuit debugger programmer in the article for part 1 of this series on the MopBots website. Just so you know, if you're using the PICkit 3, you'll need to use the MPLAB X v6.15 or version 6.15 software to get it to recognize the PICkit 3 programmer. Otherwise, you may run into issues using any newer version of the software. I go over in detail with pictures how to download that version of MPLAB in Windows in the article for part 1 of this series on the MopBots website. Again, I'll leave all the appropriate links you'll need to succeed in this project in the description of this video. Let's now look at the flowchart for this project. The flowchart is basically pseudocode for our project. It's like our notes on paper explaining how we want to configure the code to do what we want, for our project to function like we want. Starting from the top, we see the green oval shape with the while statement. This means that when the program begins, it wants to stay in this loop. When the code comes back to this point, it will run again forever. The statement basically says, while you are the number 1, keep going, which means that the 1 always stays being a 1, never changing, which always makes it a true statement. The next step in the flowchart is the green oval shape with the start label. A start label begins the sequence of events within the while loop. The next step in the flowchart is the yellow diamond shape. That's basically a decision point based on a condition. It's asking, has the button on port A at pin RA0 been pressed? If it has, then continue to the blue rectangle with the go to on statement, where it'll manipulate the data to turn the LED on. Once the LED is turned on, then the code goes back to the start label. If the button hasn't been pressed, then continue to the next yellow diamond shape that asks a question based on another condition. Has the button on port A at pin RA1 been pressed? If it has, then continue to the blue rectangle with the go to off statement, where it'll manipulate the data to turn the LED off. Once the LED is turned off, then the code goes back to the while statement. If the button hasn't been pressed, then the code goes back to the start label. As you can see, a flowchart is a diagram that helps us to understand the flow of the code that we want to write. Being able to visualize how the code should work makes it much easier to think about how we should program the microcontroller. It's highly recommended to create a flowchart for when you are planning a coding project, especially one that will contain several actions in it and a microcontroller. I left all the details about this flowchart and the meaning of its symbols in the article for part 2 of this series on the Mopbots website. Before we go over the assembly of this circuit, let's briefly go over the pins of the PIC 18F4525 that we'll be using specifically for this project. Throughout this process, we'll be referring to the schematic diagram for this project. I'll show it up on the screen from time to time, but you can go and download one for yourself so that you may follow along more easily. I'll leave the link to it from our website in the description of this video. Starting at pin 1, or the master clear pin, this will be used for our reset switch, or switch 3. If we were to look at page 43 of the data sheet for the PIC 18F4525 microcontroller, we'd see that this page explains as to what the master clear pin is for. The datasheet states that the MCLR pin provides a method for triggering an external reset of the device. A reset is generated by holding the pin low. We can see in the schematic diagram that the MCLR pin is being held high through the 1 kilo ohm resistor, or the 1 kilo ohm pull-up resistor, that's resistor R4. When the reset switch, switch 3, is pressed, a connection is all of a sudden made from the MCLR pin to ground through the switch itself. This sends a low signal to the MCLR pin of the microcontroller, therefore resetting the code back to the beginning. A 100 nanofarad capacitor, that's capacitor C2, and remember a 100 nanofarad capacitor is the same as a 0.1 microfarad capacitor. It's been placed across the reset switch, switch 3, for the use of keeping the voltage across the pins of the switch stable. If you're familiar with the resistor capacitor circuits, or the RC circuits, and their time constants, you know that after 0 time the capacitor will not drop any voltage. This is because once a capacitor is fully charged, it tends to block any changes in voltage. It takes 5 time constants to fully charge a capacitor. It also takes 5 time constants to fully discharge a capacitor. So when the switch, switch 3, has not been pressed, the MCLR pin is held high via the 1 kilo ohm resistor, that's resistor R4. Once the push button reset switch, switch 3, is pressed, it takes 5 time constants for the capacitor to fully charge. Looking at page 2 of the data sheet for the PIC 18F4525, we can see the pin diagram. Pins 2 and 3 are contained in port A of the microcontroller. Pin 2 is referred to as RA0, and pin 3 is referred to as RA1. So RA0 means bit 0 on port A, and RA1 means bit 1 on port A. Port A is one of the I/O ports of the PIC 18F4525 that contains individual I/O pins for that port. Since the PIC 18F4525 is an 8-bit PIC, it has up to 8 bits on each port, ranging from bit 0 to bit 7. Referring to pages 91 through 92 of the datasheet, we can learn that port A is an 8-bit port, and that pins RA0 and RA1 are 2 of 8 total input-output pins on port A. We see that pin 2, or RA0, is connected to a terminal of the momentary push-button switch, the on switch, that's switch 1. At that same terminal, a 1 kilo ohm pull-down resistor, that's resistor R1, is connected to ground. We also see that the opposite terminal of switch 1 from its pull-down resistor side terminal is connected to the positive power supply of plus 5 volts. Similarly, we see that pin 3, RA1, is connected to a terminal of the momentary push-button switch, the off switch, or switch 2. At that same terminal, a 1 kilo ohm pull-down resistor, that's resistor R2, is connected to ground. We also see that the opposite terminal of switch 2 from its pull-down resistor side terminal is connected to the positive power supply of plus 5 volts. So switch 1 will act as our on switch to turn an LED on. Switch 2 will act as our off switch to turn that same LED off. One terminal of switch 1 is connected to pin 2, that's pin RA0, and to resistor R1 to ground. The opposite terminal of switch 1 is connected to the plus 5 volt power supply. One terminal of switch 2 is connected to pin 3, or pin RA1, and to R2, or resistor R2, to ground. The opposite terminal of switch 2 is connected to the plus 5 volt power supply. Looking at the schematic diagram, we see that we have an LED that's labeled D1 on the schematic diagram, and a current limiting resistor, resistor R3, tied to pin 33, or pin RB0 of the PIC. For this simple LED switch project, I'm using a red LED for D1, but you can use whatever color LED you like. Notice that pin 33 is considered to be RB0 for the PIC 18F4525. This means that RB0 is bit 0 on port B. Port B is one of the I/O ports of the PIC microcontroller that contains individual I/O pins for that port. Since the PIC 18F4525 is an 8-bit PIC, it has up to 8 bits on each port, ranging from bit 0 to bit 7. So RB0 means bit 0 on port B. Referring to pages 94 through 95 of the datasheet, we can learn that port B is an 8-bit port, and that pin RB0 is one of 8 total I/O pins on port B. Looking at the schematic diagram, it's difficult to read the pin numbers for the PIC's power and ground, so let's take a look at the pin diagram on page 4 of the datasheet so we can see the VDD and VSS pins. Even though our schematic doesn't quite show this, there are 2 VDD pins, pins 11 and 32, and 2 VSS pins, that's pins 12 and 31, on the PIC 18F4525 microcontroller. We will connect both VDD pins to our positive power supply, that's plus 5 volts, and connect both VSS pins to our negative supply or ground, or 0 volts. VDD is used as the positive supply voltage. VSS is used as the negative supply voltage. Looking at our schematic, we see that we will connect both VDD pins together to the plus 5 volt supply. From this connection is a 0.1 microfarad ceramic capacitor in parallel to it and ground. This capacitor acts to help stabilize the supply voltage feeding into the microcontroller, which is crucial for its operation. Both VSS pins of the PIC microcontroller will be tied to ground, as can be seen in the schematic for this project. Pins 11 and 32 of the PIC microcontroller are its VDD pins. Pins 12 and 31 of the PIC microcontroller are its VSS pins. Both VSS pins of the PIC will be tied to ground. Both VDD pins of the PIC will be tied to the plus 5 volt supply. A 0.1 microfarad ceramic capacitor will be tied across this connection and ground to help stabilize this voltage for the PIC. Now that we have an understanding of the pins that we're using on the PIC 18F4525 microcontroller we're using, let's next get into the hands-on stuff and finally begin the process of assembling the prototype circuit. For this project, we're using a dual inline package, or PDIP, for the PIC 18F4525. The first P in PDIP stands for plastic. This means that the 40 pins that our PIC has is divided into two and are lined on both the long sides of the PIC's body, hence the dual inline package. 40 pins is a lot, and it can become quite tedious to count them every time we're making connections to them. Also, we'll need to remove and replace the PIC on the breadboard when we need to write our code to it from our universal programmer seat adapter. That's this right here. Every time we take it out and need to place it in, it becomes quite tedious to count the pins and to figure out the alignment of the pins back on our breadboard to the connections that each pin needs to be on. So to make things a bit easier, before we get to prototyping our circuit on a breadboard, I find it extremely helpful to make some marks directly on the PIC's body before I start making any connections to the pins themselves. Now, I have another PIC microcontroller here, and we can see here that I've taken a fine tip permanent marker, if I can get the lighting right. I've taken a fine tip permanent marker and I've pre-drawn the plus symbol and the minus symbol on both sides of the PIC microcontroller for pins 11 and 12 and 31 and 32. Those are the VSS pins and the VDD pins. So you can see that I've already pre-marked on the body of the PIC microcontroller, so it's easier for me to know what these pin numbers are, where the power connections are to the PIC, and for when I remove the PIC out of the breadboard and then place it into the adapter or the seat adapter here every time to program the PIC. So that kind of takes a lot of time out of having to do that, and it notifies me where my plus and minus pins are, or the power pins are, on the PIC microcontroller. And when you're doing this, there's a dimple on the, if it's faced in this direction towards you, with this dimple in the top left hand corner of the PIC's body here, that indicates pin number 1. So this would be pin number 2, pin number 3, all the way down to the last pin on the left side, which is pin 20. And then directly across from there is pin 21, pin 22, and then it proceeds up the right side of this PIC up to pin 40. As for placing the PIC microcontroller down onto the breadboard, I happen to have placed my PIC microcontroller somewhat in the middle of the breadboard here, and I've aligned the PIC to be about center, and I've placed the pins 1 through 20 to be placed in the points D D22 down to D41. Those are the points on the breadboard. So here's column D if you're looking from either end of the breadboard, and up the column here, this pin 20 for the PIC microcontroller is at point D22, or excuse me, at pin D41, and then all the way up to pin 1 of the microcontroller, it's at location or the point D22 on the breadboard. And then pins 40 through 21 of the PIC microcontroller have been placed into points. Sorry, this is pin 40 and this is pin 21. So pin 40 is at point H22, and then pin 21 is at point H41. So let me repeat that again. So pin 1 of the PIC microcontroller is right up here, and it's located on my breadboard at point D22. Pin 20, which is the lower pin on this side of the PIC microcontroller, is in point D41 on the breadboard. Pin 21 of the PIC microcontroller is at point H41, and then pin 40 of the microcontroller is at point H22. So to make the proper connections for power for the PIC 18F4525 and all the other components that it'll drive, I first started with where the 5-volt power supply will come in to the breadboard. So what I did is I started with this orange jumper wire here, and I placed it at one end at the top point on, I'm considering this side over here to be the left-hand side of the board, in the first point for the positive power rail on this side of the board. So this orange jumper wire is currently connected to the positive of the power supply, or the 5-volt power supply, which is not currently on, but that's what this orange jumper wire is connected to currently. Then I took a black jumper wire, as you see here, and I placed it into the top point on this side of the breadboard, or this side of the negative power rail of the breadboard. And that black jumper wire is connected to the ground, or to the negative supply of the power supply. So from there we have our two initial connections from our power supply going into the breadboard, the positive and the negative. And then what I did next was I placed a 0.1 microfarad ceramic capacitor, and I placed its legs into the points E4, and I placed the other leg of the capacitor at point G4. So that crosses this center gap of the breadboard. And then to continue the connection from this leg of the capacitor, I put this yellow jumper wire in, and it's one end of it is at point B4, and the other end is at a point that's adjacent to it into the positive power rail of this side of the breadboard. And similarly, to continue the connection to negative or ground, I've connected this green jumper wire that's in line with this leg of the capacitor at point H4, and I placed the other end of the jumper wire at a point into the adjacent negative supply rail on this side. To continue the positive supply all the way down this breadboard, there's from this side of the breadboard on the positive power rail, and the same for the negative power rail, and to this side of the positive power rail and the negative power rail, this center gap here, which you might not be able to see clearly right now, these two sides of the power rails are isolated until I made the connection for both the positive with this yellow jumper wire going from a point on this side, it doesn't matter, but some point on this side, and continued that connection to some point on the left side, or my left side. So that's to continue this positive power rail all the way through on this side of the breadboard. And similarly, I connected this brown jumper wire on the negative power rail to continue this whole length of the negative power rail. And then that negative connection comes from this longer green jumper wire here, and then it's connected from this side to this side. That connects the grounds, and the same for the positive. I've got this red jumper wire here that connects this side positive power rail to this side positive power rail, and these connections continue up to this side. And then I have a yellow jumper wire continuing the connection from my left of the positive power rail here over towards the right side of the positive power rail all the way up into the end. And the same for the negative power rail, continuing up through here on this side, continues that path through this brown jumper wire on towards this side, and that's connected to the black jumper wire here. So to kind of recap what's going on there, we have our positive. Once the power supply is turned on later to turn the circuitry on, you have your positive side connection going through this orange jumper wire, continued down this side of the positive power rail through this yellow jumper wire to continue to this side of the positive power rail, across this red jumper wire to this end of the positive power rail on this opposite side of the breadboard. That connection continues through this yellow jumper wire here, and it continues that connection all the way down to the end of this side of the positive power rail. And similarly, we have our negative supply here from the power supply, and it's connected to this black jumper wire, and that negative supply is continued through the negative power rail on this side of the breadboard through this brown jumper wire to this end of the negative power rail, across this green jumper wire, and then continued down from this side of this negative power rail through this brown jumper wire, and continues down this end of the negative power rail to the end of the breadboard here. What I did to continue off the positive power rail here, I have this yellow jumper wire going to point, I believe that's point B32, and that's in line with pin 11, and that is for the positive supply to come into the PIC microcontroller, and the other end of that jumper wire is connected into an adjacent point on the positive power rail here. And then I connected the negative supply at point C5, I believe that point is, and the other end of this green jumper wire is in a point on the negative power rail here, and this green jumper wire is in line with pin 12, and that is for the negative supply to the PIC microcontroller. And similarly, on this side of our plus and our positive and negative supply to the PIC microcontroller to pins 31 and 32, I've got this yellow jumper wire here going to point J30 that's in line with pin 32 of the PIC microcontroller, and that's to the positive supply pin of the PIC. And then I got this green jumper wire here that's at point J31, and the other end of that jumper wire, the green one, is in a point adjacent to it in the negative power rail, and that green jumper wire is in line with pin 31 of the PIC microcontroller, or the other negative supply pin to the PIC microcontroller. So now that we have the power supply set up to the breadboard and to the PIC, let's move on to set up the MCLR connection, or the master clear pin, that's pin 1 of the microcontroller, which will be for our reset button for the PIC. To make the MCLR connection for the reset button for the PIC microcontroller, I took a 1 kilo ohm resistor and placed, I don't know if you can see it, but it's this resistor here, and placed one of its leads in line with pin 1 of the PIC microcontroller in point B22 on the breadboard. I placed the opposite lead of that 1 kilo ohm resistor into one of the neighboring positive power supply points on the breadboard, or the positive power rail. Next, I took a blue jumper wire, and I'm not sure if you can see that in the camera, but it's right here, and I have one leg of that blue jumper wire is placed into point C22 on the breadboard. That's also in line with pin 1 of the PIC, and the other leg, or it's in line with the PIC and the that 1 kilo ohm resistor. And I placed the opposite leg of that blue jumper wire at point C17 on the breadboard. Next, I took a 2-terminal momentary push button switch, and I placed one of its leads at point D17 in line with the blue jumper wire, and the opposite lead of the switch into point D15 of the breadboard. Now that the switch is in place, I took a 0.1 microfarad capacitor and placed its terminals in line with the terminals of the 2-terminal momentary push button switch we just installed on the breadboard here at points B17 and B15. To complete the connection for the reset button, I took a green jumper wire right here and placed one of its terminals in point A15 in line with the capacitors and the switch's terminals on the same row. And then I placed the other lead or leg of that little green jumper wire into an adjacent point along the negative power rail of the breadboard. So I mentioned that resistor earlier, that 1 kilo ohm resistor. This is resistor R4 from the schematic diagram. This is, like I said before, this is pin 1 that we're connecting that 1 kilo ohm resistor to. That's resistor R4. This is going to be our master clear pin, and that blue jumper wire goes to this push button switch, which is switch 3 on the schematic diagram, and then this 0.1 microfarad capacitor is a capacitor C2 as referenced on the schematic diagram. So next we'll discuss the connections of pins 2 and 3 of the PIC microcontroller. Okay, now we're ready to make the connections for what will be our on and off switches. To start with, let's begin with switch 1 on our schematic, and we'll look and see where it's placed on the breadboard, and then we'll do switch 2. So switch 1 will end up being the on switch, and switch 2 will be the off switch. So in this case, looking at the breadboard here, this switch here is switch 1, and this switch here is switch 2, just so we have that reference as I'm talking along here. So I took one of the 4-terminal momentary push button switches. So these 2 switches have 4 legs or leads on them instead of 2 like this one. So this is switch 1 and this is switch 2, and again they both have 4 terminals where they will be isolated from each other. I placed one terminal at point E12, so this is column E, and this is terminal 12 or leg 12 of this switch 1 here, and this leg over here is at point E10 of the breadboard. For the opposite terminals of button or switch 1, I placed those legs into points F12 and F10 So these two legs are isolated from these two legs or leads of the switch across this groove or center gap of the breadboard. So they're isolated on either side. And like I said, this is switch 1 as referenced from the schematic diagram. And then next I took the second momentary switch and placed one side of its terminals onto points E7 and E9, and the opposite terminals are at points F7 and F9. And again, both these sides are isolated from each other. And this is switch 2 as referenced on the schematic diagram. Now moving on to the connections of these two switches, I started with the plus 5 volt power supply to both of them. I took a small yellow jumper wire and made a connection between the two switches here. So this, if we're referring to this yellow jumper wire first, this yellow jumper wire, I have one leg of that jumper wire at point G10, and that's in line with this leg of switch 1 that was at point F10, and the other leg of this little jumper wire is in line with this leg of switch 2 at point the jumper wire leg is at point G7, in line with that leg of switch 2 that's at point F7. And then continuing those two connections from both of those legs of the switch 1 and 2 to the plus 5 volt supply, I've got this other yellow jumper wire where I have one of its legs at point J7 and the other leg of that jumper wire is in an adjacent point along this positive power rail here. So that makes the connection of the plus 5 volt supply going to both switch 2 and to switch 1, just like it is referenced on the schematic diagram. Next, moving on to the connections coming from the PIC to the switches. For switch 1, I took this yellow jumper wire here, and I connected it to a point in line with pin 2. That's at point C23, and the other end of that yellow jumper wire goes to a point D12, and that point is in line with one of the legs of switch 1, and that was the leg at point E12. And then I took a 1 kilo ohm resistor and placed one terminal into point B12, which is in line with this yellow jumper wire going to pin 2 of the PIC microcontroller, and it's in line with the leg of switch 1 at point E12. And then the other leg of that 1 kilo ohm resistor is in an adjacent point along the negative power rail. And then similarly, for the connection from pin 3 of the PIC microcontroller, I have this orange jumper wire here, and I placed it into a point B24 that's in line with pin 3 of the PIC microcontroller. The other end of that orange jumper wire goes to a point D9, which is in line with switch 2 at point E9. And again, I took another 1 kilo ohm resistor and placed one of its legs into point B9, which is in line with that orange jumper wire and also in line with switch 2. And the other leg of that 1 kilo ohm resistor is at an adjacent point on the negative power rail. So the resistor I just talked about that goes in line with switch 2 and pin 3, that was our resistor R2 as referenced on the schematic diagram. And this resistor here that's in line with switch 1 and in line with that yellow jumper wire going back to pin 2, that is resistor R1 as referenced on the schematic diagram. So next we'll move on to the connections of the LED to pin 33. So to complete our prototype circuit, all we need to do now is make the connections for the LED. We'll control with the two switches here. That's switches 1 and 2 that we just previously added to the breadboard. So what I did is I took an orange jumper wire that could reach from point J31 that's in line with pin 33 of the PIC microcontroller all the way over to point J20 of the breadboard. So this orange jumper wire reaches from point J31 of the breadboard all the way over to point J20 of the breadboard. And that, again, this orange jumper wire is in line or connected directly to pin 33 of the PIC microcontroller. And the other end of that orange jumper wire is in line with the anode of the red LED, and that anode leg is at point I-20 of the breadboard, and then the cathode of this red LED, which I know you probably can't see from that angle, the cathode of the LED goes into point J17, and then we see this resistor here, and this resistor is a 220 ohm resistor. This is resistor R3 as referenced on the schematic diagram, and I have one of its legs or leads in point J17. That's in line with the cathode leg or lead of the LED, and I have the other leg of this 220 ohm resistor going to an adjacent point along the negative power rail on this side of the breadboard. So now that the connections have been made to the pins of the PIC on our breadboard prototype circuit, we're ready to begin the process of creating the code for the PIC. We did this in part 3 of this introduction to PIC programming using C, programming a super simple LED switch project. There you can find not only the code for this project, but the instructions on how to use the PICkit 3 programmer and MPLAB software to compile the code and upload it to your PIC microcontroller. The links will be left in the description of this video. So once you've gotten the code, compiled it, and loaded it to your microcontroller, you can place the PIC back onto the breadboard circuit. Make sure that you've placed it into the correct points. Then all there's left to do is just turn the power on to your circuit. And then we can see if everything's working as it should be. So now that we've walked through the connections here, and like I said, we've already uploaded the code to this PIC microcontroller, let's go ahead and connect it to the power supply. I'll move the camera into a closer position so you can see everything a little bit better, and then we can kind of view on how this circuit is going to work. I won't say anything during that. I'll just show you the circuit working, and I'll also lower the lights a little bit so it's a little easier to see. So let's do that next. Well, I hope that you enjoyed this project. I really enjoyed it. I think it's a real neat project, and it's a good way to get started into learning how to use PIC microcontrollers. And I love using PIC microcontrollers. They're a lot of fun, and there's a lot to learn with them. I don't know, I still feel like I hardly know anything about them because there's so much to learn about them, but they're a lot of fun. So I hope you tried out this project. I want to thank you for joining me for this project. Again, I hope you enjoyed it with me. If you haven't taken the plunge yet to try this neat circuit out, I encourage you to do so, or try any number of projects available at MockBots and start learning and making with electronics. All you have to do is make the decision to get motivated and start doing today. Again, thank you for joining me, and remember to keep at it and stay motivated.